this video, I would like to solve two examples regarding the summation. The first one, find the value of the summation sigma k from 0 up to 14 of sine of pi k. Okay, so I'm just gonna write this series, and then I just need to plug in k equals to 0, k equals to 1, 2, 3, up to 14 into the function that is inside the sigma. So I have sine of, instead of k, I just started with 0, so 0 pi, plus sine of, just plug in 1 pi, then 2 pi, then 3 pi, and it goes up to 13 pi, and then sine of 14 pi. Okay, so the series is finite up to 14, so it's manageable. I can solve it. Now I just need to find the sine of 0 pi, pi, 2 pi, 3 pi. I'm gonna start by just giving you a recall of unit circle. If I have the unit circle, this is 1, this would be cosine axis, this would be the sine axis. And then I have different coefficient for pi. So pi starts at here is 0, and then pi would be this angle. Okay, so 0 pi would be just 0. So I have sine of 0. I know that sine of 0 is 0 because the 0 angle would be here, sine of that is 0. Then I have sine of pi. Pi would be this angle. Let me write this. And then as you see, the sine of that would be 0. And then sine of 2 pi. Where is 2 pi? This is pi, and then up to here, starting at here up to here, it would be 2 pi. And as you see, the sine of 2 pi is again 0. Sine of 3 pi. So starting at here, pi, 2 pi, 3 pi would be here exactly like pi. Then it would be 0. All of them are 0, as you see. And so the answer for this sum would be 0. Okay? If I had cosine of pi k, and then if I had cosine for any of them, then cosine of 0 would be 1, cosine of pi would be -1, and then cosine of 2 pi is again 1, and then I get 1, -1, 1, and -1, and then still it would be 0, but this one is just sine. Okay, let's go to the second question. Given Rn as 2 over n sigma of a function of I starts at 1 and it goes up to n, we need to find the limit of Rn as n goes to infinity. Okay, so to solve this question, we just notice that we have a sigma and then the limit of that. It's recalled the definite integral, if you remember. Let me write the formula for that. If we have the integral of f of t dt, or actually let me just put f of x dx. Both of them are correct. From a number a to a number b, okay? So how do we evaluate this definite integral? This is called definite. It's just because we have lower limit and upper limit for integral. Then we have the interval a and b, like this. Actually, let me graph it. Oops. I'm gonna graph it like this. This is x-axis, this is y-axis. Assume that this is a function f, this is a, and then this is b. This integral gives us the area below the graph of f over x-axis between a and b. Okay, so this is just calculating this area, and to calculate that using Rayman sums, the idea was like that. If we have a to b, we're just gonna divide this interval into n sub-intervals like this. Okay, n of them, and then in each of these intervals we're gonna pick a sample point. We can usually pick it like the right endpoints, which would be on the first subinterval. It would be this number in here or this one in here, if we choose the left endpoint or the middle point, whatever. But we pick a sample point, and then we're gonna use the value of that function over that sample point. It gives us the height. Then we have the width times the height, and then this gives us the area of this small rectangle. We're going to calculate for all of them the height, and then we have the width. We just calculate the area of each of them, and then we just add them up. It gives us the area of the whole thing. Okay, so we have what? We have delta x as b minus a divided by n. This gives us the width of the rectangles. And then for the height, we're just plugging the sample point. This is our sample point. We're just going to plug it into the function, and it gives us the height of each of these small rectangles. And so we just have f of xi star times delta x. This is the area of each of these small sub rectangles. We're just going to add them up, from 1 up to n, and then to have an accurate integral, we're just going to need to take the limit as n goes to infinity. This is called Rayman Sum, and this limit is going to define the definite integral for us. Now look at Rn that is given, and then compare it with that. Okay, delta x that we have in here, it would be b minus a divided by n. As you see, it doesn't have any I in it, so it is not related to the counter of our summation. That's why we can bring this out and then put it out of the summation, because it doesn't have any I in it. So as you see here in our Rn, if we just compare, this would be our delta x. Okay, so delta x is 2 over n, which is b minus a divided by n. Okay, so I know that the difference between the a and b here is just 2. Okay, now look at inside the summation. Inside the summation, what I have is f of the sample points, okay, that I chose. Now, if I want to be starting and looking at my sample points, let me actually have a better a and b interval. This is a, b. We're just gonna divide them into sub-intervals like that, okay? This is delta x, which is 2 over n. And then, what is this point in here? This point in here is actually a plus 2 over n, right? Because this length here is 2 over n. So this one is here is a plus 2 over n. Now, what is this one? This is a, and then I have 2 over n, the length of this subinterval. I have another 2 over n in here. So this is here is 2 times 2 over n. It's just because this area that I have here, this interval, is also 2 over n. I have another 2 over n. So together, what I have, let me use blue color, a plus 3, 2 over n. Okay, so this is a, 1 2 over n, 2 2 over n, and then this is a plus 3 2 over n. You get the idea, right? And then we go up to b, which would be what? Which would be a plus n, because we divided the interval of a and b into n subintervals. 2 over n. Okay, and as you see, this n is going to be cancelled out with that one. That's why b is equal to a plus 2. Okay, this is something that we realize that. Okay, now I just compare this one with the points that I get in here, and I see that this is my a plus, if I just plug in 1 in here, I get 1 2 over n. If I plug in 2, I get 2 2 over n. Plug in 3, I get 3 2 over n. As you see, these are my sample points. Okay, let me just put here that these are my xi stars, and this is my xi stars, the sample point that I chose for my summations. So I can say that my f of x is equal to what? It's equal to 5. You see, you just plug in your sample points into your function. So instead of any x in your function, you just need to plug in your sample point. So it would be 5 times x, and then I see a power 3 over here, and then minus 6, and then I see x to the power of 2. So x to the power of 2. Okay, and then based on my sample point, I see that, actually, let me just put it in here. I see that a would be 2. You see, a plus 2 over n. So this is a. And I know that the difference between a and b is equal to 2, just because of comparing this. And so based on that, b is equal to 4. That's why the limit of our n as n goes to infinity, based on the definition of the definite integral, is the integral from 2 to 4 of the function fx, which is 5x cubed minus 6x squared dx. Now let's calculate this integral using power rules, which would be what? 5x to the power of 4 divided by 4 minus 6x cubed divided by 3, and it is from 2 to 4. Just plug in 4 for any x, minus plug in 2 for any x. So it would be 5 over 4, and then 4 to the power of 4 minus 6 over 3. I can simplify that one, and then I get a 2. It would be 2 4 cubed minus, and then plug in 2 into here. It would be 5 over 4, 2 to the power of 4 minus, plug in 2 into here, so it would be 2 cubed. Okay, and the answer is a simple algebra that you can calculate.